Hello, gentlemen. Welcome back to Calc 11. Guys, as promised yesterday, we're going to slow it down today a little bit and just focus on practicing our EVT and MVT questions. However, we're also going to throw a little bit of a throwback in here of the IVT. All right, this first page, guys, is a little bit of a study guide for you. What it does is it re-summarizes all three of those theorems for you. All right, so you can see the first line is your IVT, MVT, and EVT. Guys, I'm going to start at the bottom and just rediscuss again the EVT here. Notice there's the formal definition column. If a function is continuous on a closed and bounded interval from A to B, then f has to obtain a maximum and a minimum each at least once. Basically, when you're looking at the center column here, guys, this is the non-mathematical way to kind of like describe it. It says every continuous function on an interval, right, has a highest y and a lowest y. Okay, that's your EVT, extreme value theorem. On the last column over here, you'll see any conditions that need to be checked. In this case, it is just continuity. Moving up back to your MVT, remember we learned that yesterday. This is where we're saying that there's at least one point where the slope of the secant line equals to the slope of the tangent line. Right? The slope of the secant line equals the slope of the tangent line. Remember, this is your secant line and this is your tangent line. All right. It also indicates a point where the average rate of change is equal to the instantaneous rate of change. Remember, this is your average rate of change and this is your instantaneous rate of change. Conditions for this are continuity and differentiability. Remember, continuity is on the closed interval, and differentiability is on the open interval. This one, guys, is a little bit of a throwback, okay? Intermediate value theorem. If you recall, intermediate value theorem said, if A is a continuous function f with an interval from A to B as its domain, and it takes on values of f of A and f of B at each end of the interval, then it also takes on any value between f of A and f of b at some point within that interval. Because there's at least, basically it's saying that there's at least one number c between a and b such that f of c is greater than f of a but less than f of b, or somewhere in between those two at least, okay? So it could be reversed in terms of which one is bigger and which one is smaller, but again, it's somewhere in between those two. And the condition for that was just that the function was continuous. Just had to be continuous, and that was really it. Why am I throwing back in the IVT? Why are we going here? Because, guys, the AP, when they're giving you questions about your IVT and about your MVT, and they're asking you, especially multiple choice questions that deal with this concept, students always confuse the two of them. All right, students always confuse the two of them. When you're looking at your IVT gives you some sort of function, f of x, and it's asking you, does a value on the function exist? That's what they're saying, right? Intermediate value theorem says, do I hit all the y values? Okay, so if I'm giving you a value for your function and I'm asking you if a value on the function exists, then that has to be your IVT. The intermediate value theorem, though, is a little bit different, and this is where students get confused. The IVT gives you the original function, and it's asking you, does a value on the derivative exist? It's asking you, is there an f prime of c that equals to some number? Okay, so again, IVT gives you a function, asks you if a value on the function exists. MVT gives you a function and asks you if a value on the derivative exists. And remember, values on the derivative requires differentiability, which is why that is an extra condition here to be able to use your MVT. All right, let's take a look at some examples and let's take a look at the difference. Notice here, okay, two functions f and g are given, and it also says here that they're differentiable. Remember that if two functions are differentiable, therefore they're continuous. What that is telling us is that actually any three of these theorems up here, the MVT, IVT, or EVT, all of them apply. Okay, let's take a look. It says g is also strictly increasing. The table above gives values of the function and the first derivatives at the selected values of x. The function h is given by this, f of g of x, and then minus 6. First question here says, explain why there must be a value, okay, r, where r is in between 1 and 3. Okay, here's my interval, all right, where h of r has to equal to negative 5. Take a look, guys. They gave us an original function. They gave us h, and they're asking us, does there exist a value for h? H of r. Does h of r equals to negative 5? This here, gentlemen, is an IVT question, right? They're asking me, does a value on the function exist? Well, here's the deal. Since f and g are continuous, right? That means that h of x is continuous. So the IVT applies. Okay, now since we know the IVT applies, let's check out the values of those endpoints. First, I need to find h of 3. Remember, h of 3 is f of g of 3 minus 6. That's the case. G of 3, using our table, that is 4. F of 4 minus 6. F of 4 is negative 1. Negative 1 minus 6 is a negative 7. Check out h of 1. That's f of g of 1 minus 6. G of 1 is 2. So we have f of 2 minus 6. F of 2 is 9. 9 minus 6, that is equal to 3. Now, guys, if you take a look here, your two y values are going from negative 7 to positive 3. Negative 5 is right in between them, right? So we're going to now say, since, right, negative 7 is less than negative 5, which is less than 3, right? There exists an r, so I'm just recopying question, such that, I really should say on the interval, because remember that's part of the theorem. So it's on 1 is less than r is less than 3, okay, such that h of r is equal to negative 5. So again, this was your IVT. Now, if we take a look at the second part here, okay, it says, explain why there must be a value c between 1 and 3 such that h prime of c equals to negative 5. Guys, this is completely different here. Now they're asking you what is going on with h prime of c, okay? When I give the original function and I'm asking you for the existence of the derivative, this is going to be your MVT, okay? So all I'm going to do is really kind of like recheck my conditions, okay? They really want my conditions to be checked. And here we go. Just going to say, since they are differentiable, oh no. There we go. Let's move that a little further down. Since f and g are differentiable, therefore they're continuous, right? So I'm just going to add in that other condition here that we need and that we discussed, okay? Since f and g are differentiable, okay, they are therefore continuous. Continuous is on the next line. So which means that h of s is continuous and differentiable. So basically applies because h of x is made by f and g. Okay? Once we know that, then we can say that the MVT should apply on that interval. Okay? And let's double check it out. Remember our rule, right? Our MVT, that is basically h of b minus h of a over b minus a, just changing to h's to match the question, has to be equal to h prime of c. In this case, they gave us c. So let's take out. We got h of 3 minus h of 1 over 3 minus 1. That's a negative 7 minus 3 over 3 minus 1, or negative 10 over 2, which equals to negative 5. Hey, that matches. That sounds pretty good. Okay, so when you're looking here, this is telling you, okay, therefore, there must exist a C, and specifically on that interval between 1 and 3, okay, such that H prime of C equals to negative 5 by the MVT. Okay, guys, this is actually an AP question. All right, these are one free response question. I forget what year it's from. Okay, but this literally is an AP question. Just going back and stating the theorems that you know, stating your conditions. Conditions are part of the scoring guidelines for those questions, and then answering from there in full sentences. Okay, guys, moving on to a little bit more practice here on question number 2. It says, for each of the following questions, determine whether the statements must be true, whether they might be true, or whether they cannot be true. Because this is a great exercise in justifying your information, okay, and seeing what is happening, all right? So let's take a look at letter A. Letter A says f of 1 is less than 0, or it's negative, and f of 5 is less than 0, which means that it's negative, right? So if I were to draw a sketch here, I get f of 1, which is somewhere down here. F of 5 is also somewhere down there. This says, then there must be a number C in between 1 and 5 such that f of C equals to 0. Guys, that doesn't have to happen, right? It doesn't must be true, okay? Maybe the graph looks like this. Maybe the graph looks like this. Or maybe the graph isn't even continuous. They said nothing about continuity. So maybe the graph looks like this, and it starts back over there and goes like that. So again, this might be true, but we don't know. There's not enough information to tell us what is going on, okay? Take a look at part B. It says if f is continuous, oh, see, there's that special information right there. Continuous on 1 to 5. That gives us a lot of information, okay? Then it says f of 1 is negative and f of 5 is negative. Then there must be a number C between 1 and 5 such that f of C equals to 0. So it's kind of the same scenario, but it was really nice of them now. They told us that the function is continuous. But now that it's continuous, the only difference is that red scenario, not even a possibility anymore. This could be a possibility, right? This could be a possibility. Sorry, excuse me. Okay, but the discontinuous one is not a possibility. However, going back to the question, does there have to be a point where f of C is equal to 0, the value is 0, right? I don't know. There might be. There is a scenario where it could happen, all right? But it doesn't have to be true, and it's not impossible. Now let's take a look here, okay? It says if f is a continuous function. All right, we got another continuous function here, okay, on 1 through 5. And f of 1 is 2 and f of 5 is 2. Ooh, this is interesting, right? So f of 1 is 2. And we have f of 5 is 2. Then there must be a number C in between 1 and 5 such that f prime of C, ooh, the existence of a derivative, guys, f prime of C is equal to 0. Here we go. They're giving you values for f, and they're asking you, does f prime of C exist? When I see this, I think MVT. Okay? And here's the deal. They did tell you it's continuous, but they did not tell you that it's differentiable. So if you go through and you automatically apply your MVT and you're like, yeah, this works because I could just make like, a curve, and here my derivative is equal to 0, and yeah, we're fine. You're forgetting about the fact that they didn't tell you that it's differentiable everywhere, right? Maybe this function looks like an absolute value and it has a point there. Maybe it looks like a cusp, right? And it looks like a bird between those 2 points, all right? So therefore, does there have to exist a c? Well, there might. We don't know. It's a possibility, but it doesn't have to happen. Take a look here though. Okay, take a look at the next one. The next one says is if f is differentiable on the closed interval. Ooh. And now they're telling us f of 1 is 2, right? F of 1 is 2 and f of 5 is 2. There must be a number c such that f prime of c is equal to 0. Now guys, remember, again, I'm thinking if they give me a function, they're asking me about the derivative, I'm thinking MVT. Okay, but now they told you that the function is differentiable, which means that it has to be continuous, which means that my MVT now applies. So this statement just went from a maybe to a must. This must be true. Because it's differentiable, I can't have that corner or that cusp. That has to be nice and smooth, and there has to be a point where we reach a derivative equal to 0 or a maximum. Okay, so keep that in mind, guys, as you're going forward. Always read and check your conditions. Take a look at letter E. It says, if a graph of a function has 3 x-intercepts, then it must have at least 2 points where its tangent line is horizontal. Guys, that is not true. Think about a graph that would look like this, okay? This graph has 1, 2, 3 x-intercepts. Says nothing here about the graph being continuous. Says nothing here about the graph being differentiable. Okay, so therefore, here's a graph, okay, where you have 3 sections and 3 x-intercepts. However, it's not continuous. And therefore, there's no 2 points where it has a tangent line that is horizontal or where your derivative equals to 0. So I could make a scenario where that is true, okay, but it's not true in this case. So therefore, this answer would be a might. It might happen. Don't know, would have to know the function, would need more information, but as of right now, don't know. Guys, one last thing we're going to be covering today, okay, we just got a little bit more here, is a special case of the MVT, right? Special case of the mean value theorem for derivatives, and it's called Rolle's theorem. You guys actually already saw it right here in part D, okay? Just take a little look back in part D. If you recall here, guys, okay, we were talking about it being differentiable and continuous, okay, and the existence of a derivative. Notice here we're talking about the derivative equaling to 0. And when we have a derivative that equals to 0, that's usually when we have a horizontal tangent line, right? And when we have a horizontal tangent line, that usually means that we reach a maximum or a minimum, as long as we're changing from increasing to decreasing or decreasing to increasing. So the condition for this to happen is, take a look at the end. Notice that the 2 y values at the end, f of 5, is equal to f of 1. So when you go to do your f of 5 minus f of 1 over 5 minus 1, you wind up getting a 0 on top of your fraction, which means that your derivative must also equal to 0. Remember, again, derivative equal to 0, horizontal tangent, possible max and min. The Rolle's theorem is just a special case of the MVT where the 2 endpoints are actually equal to one another. Not only does it say that the derivative has to equal to 0 at some point, it also implies that there might also be a maximum or minimum on that interval as well. Take a look here, okay? If y equals f of x is a continuous function on the closed interval and is differentiable everywhere on the open interval, that sounds a whole lot like the MVT. And if f of b equals to f of a, so again, if the 2 endpoints have the same value, then there are at least one number c in between a and b such that the derivative is equal to 0. Guys, this is the MVT, just that special case where the endpoints have the same value. Graphically, this means that a continuous differentiable curve has a horizontal tangent between any 2 points where it crosses the x-axis or anywhere where the 2 y values are the same. Doesn't have to be the x-axis, it could also be 2 y values that are up here like that. Okay, so let's take a look here, guys, at some examples. For number 3, it says, for each of the following graphs, determine if the MVT applies over the interval. I could even change this word here and say, guys, determine if Rolle's theorem applies. Because if you take a look here, okay, notice this y value, okay, is the same as that y value on that interval, okay? So notice when I'm looking at this graph, heck yeah, it's definitely continuous, great, but then I check differentiability. Remember, this is a problem area, okay? This is that point. This is your absolute value point, okay? It is not differentiable on that interval. Therefore, your MVT does not apply. And it doesn't even matter, gentlemen, that the two endpoints have the same value. Doesn't matter, okay? Take a look at the next one. Again, my two endpoints on my interval have the same value. And if you look at that and you think about it and you're like, all right, maybe the MVT or maybe Rolle's theorem will apply, check your conditions. Is it continuous? No, it's not even continuous. So it's not continuous. Again, MVT does not apply. I'm not even answering that question any further by just saying it does not apply. Okay? All right, let's take a look, guys, at number 4. Okay, number 4 says find the values of C that satisfies Rolle's theorem. If you take a look at A, okay, again, we're checking the same conditions as yesterday. First of all, this graph is continuous. It's a polynomial. And it's differentiable. It's a polynomial. Now here's the deal. We just need to check the values of the endpoints. Let's check f of 1. F of 1 is 1 to the third minus 1. That's 0. Let's check f of negative 1. That's negative 1 to the third minus a negative 1, which is negative 1 plus 1, which is 0. Since the endpoints are the same, that means that your average rate of change, your f of b minus f of a over b minus a, that will all be equal to 0. Okay, remember f of 1 minus f of negative 1 over 1 minus a negative 1. Okay, that whole thing is going to equal to 0 because 0 minus 0 is just 0. Notice your denominator is still 2. Our derivative, our f prime of x, this equals to 3x squared minus 1. So remember, this has to be our 3c squared minus 1. Okay, remember, we were saying yesterday, I'm just going to write the c so that it stays with the theorem, okay, instead of an x. I'm going to add my 1 over. This is 1. Divide by my 3, okay? 1/3 equals to c squared. And then we square root both sides. So c is equal to, don't forget your positive square root of 1/3 and your negative square root of 1/3. Now you can absolutely rationalize that, okay? Remember, like I said the other day, AP kind of doesn't even care if you rationalize, but I just want to justify to you, gentlemen, that this value is about 0.57 and negative 0.57. Technically, I'll just go up a little bit because it doesn't round down. But notice both of those numbers, okay? Notice both of these numbers are on your interval. Don't forget the last and final step is to check that you're on the interval. And since those two numbers are on the interval, they're both your answer. There are 2 points where you have horizontal tangent lines on that interval, okay? So again, this is really just the MVT theorem. The only difference is, okay, that the two endpoints have the same value, which just means that your derivative has to equal to 0, which means you would have a horizontal tangent. Going on to part B, okay, f of x. F of x here, okay, putting in numbers between your intervals. Let's check continuity. Uh-oh. Guys, I'm focusing on here, and I already see, okay, this is undefined at 0, okay? Since it's not continuous, it's not even continuous on the closed interval, okay? Rolle's theorem does not apply. Okay, and that is the end of that. You don't even have to go any further, all right? Always check your conditions first, gentlemen. Your job today, okay, is to go through and practice the difference of the questions. There's some MVT questions, there's some EVT questions, there's some AP questions asking about the existence, there's some reading questions and just understanding what it means, okay? However, guys, let me make a note here, especially based off of what we saw on some of the review sheets. The multiple choice, guys, okay, all right, when you're going through them, write a little explanation, right? Write why this is true. Write the theorem that you used, all right? Don't just be circling answers without a thought process, all right? Make sure that you understand. And guys, we'll hit these when we come back to class tomorrow, okay? Want you guys to bring questions, see what questions you have, what you want to go over before we move on to the next topic, because you will be getting a quiz on this next week or in this current week, depending on when this is your async. All right, but we're done with learning these theorems. This is the last day that we are looking at stuff in terms of new questions. So again, complete this activity to the best of your ability. Bring it to class and see what questions you have before we move on to our next topic. I'm looking forward to seeing you guys next week. Take care.